Hi everyone, my name is Hong Jin and thanks for coming to this talk. I will now talk about our work entitled Adversarial Specification Mining. This work was first published at the Transactions on Software Engineering and Methodology. There's been many studies on mining software specifications, in particular on automaton-based specifications. Recent work include DSM, which uses a deep learning-based approach to characterize a program state. These techniques usually take execution traces as input and as output produce finite state automaton. One problem is that they rely on the traces, and the traces have to be representative of software behavior, but uncommon behaviors may be missing in these traces. This could lead to inaccurate inferences, leading to specifications that are incorrect. In prior work, it has been proposed that test generation can help. For example, in DSM, because they use a deep learning-based approach known to be very data hungry, they produce a large amount of data by using a random test case generator to produce a large number of random test cases. To address the problem of limited traces, we suggest that more traces isn't enough, and there is a need for systematic diversification of the traces. In this study, we ask ourselves the question, given that we have traces that may not be sufficiently diverse, what can we do to address this lack of diversity? We propose a framework that we term adversarial specification mining, and we implement this framework in an approach that we term DICE, diversity through counterexamples. So we have an initial set of traces. We first mine an initial specification. In DICE, this specification would be linear temporal logic properties. And then as the initial set of traces were not sufficiently diverse, they do not capture some behavior that is essential to the software system, and this could lead to the inaccurate inferences, causing us to have some properties that are not true of the software system. In other words, we would be able to generate counterexamples to these specifications. And that is the goal of our second step, in where we try to find traces that would falsify the specifications in the first step. In DICE, we try to do this using search-based test generation, and we generate test cases that when executed will give us traces that are counterexamples to the specifications. And finally, in the third step, using the traces that are counterexamples, and along with the original set of traces, we infer a new automaton specification. Our work is essentially the use of search-based test generation to target gaps in the diversity of the initial traces. And we try to search for test cases that falsifies properties that are inferred from the initial traces and they seem to hold initially. Here is a graphical illustration of this process. Given we have a collection of traces, we try to infer some properties from them. And these are properties that seem to initially hold and are not falsified from the initial set of traces. Afterwards, we try to find counterexamples to these properties, and to do so, we use evolutionary test generation to produce test cases and collect the traces from the execution of the test cases. And this will give us some counterexamples to the properties. In DICE, these properties would be linear temporal logic properties. For instance, in this example, we have a property that says that event A is never immediately followed by event B. And so we pass this to the evolutionary test generator, and we try to produce a test case with a trace where A is immediately followed by B, or in other words, a counterexample to this property. And along with the original set of traces, we have the new counterexample trace, and we use these new traces in order to construct and infer a finite state automaton. In DICE, we use test case generation based on insights from prior studies. So we target LTL properties because in prior work has shown a relationship between linear temporal logic properties and FSA inference. Studies have shown that you could mine LTL properties and use them to more accurately steer the inference of an FSA. And prior work has also shown that you can compose linear temporal logic properties into a larger FSA. We built on top of the notion of state abstraction from the work of Picasso et al., and we use the enabledness of methods to characterize a state. And each state is one combination of enabled methods. We also build on top of the work of search-based test generation. Typically, search-based test generation is used to try to cover code elements, such as lines and branches. Search-based test generation treats the coverage of search goals as an optimization problem, using a genetic algorithm to generate and evolve test cases over time to maximize line and branch coverage. In DICE, we build on top of this work, but rather than using search-based test generation to cover program elements, our objective is to use it to falsify the LTL property. We construct one search goal for each property, and each goal represents the falsification of a property. And as before, we use a genetic algorithm. We treat the problem as an optimization problem, trying to evolve test cases over time to cover these goals and falsify the properties. To do so, we need to be able to evaluate the fitness of a trace with respect to a property. We provide the following formulation, and this is how we compute the fitness of a trace with respect to a property in DICE. Our objective is to have a trace that falsifies a property. So if a trace falsifies a property, it has the highest fitness with respect to this particular property. And if the trace does not falsify the property P, but we favor it if it instead supports the property P, or in other words, it is an example of the property. If the trace neither falsifies nor supports the property, then we favor it if it contains an event that is described in the property P. The idea here is that this trace would then be somewhat related to the property. And otherwise, if it neither supports the property nor falsifies it, nor contains any event in the property, it is completely unrelated and we grant it the lowest fitness score. The idea here is that we start off with a population of test cases and we select for tests over time such that it will contain test cases that are related to the property, and then after even more time, it would support the property and then it would falsify the property afterwards. In DICE, a single trace is a sequence of methods called on a single object instance. Since a test case can have multiple objects in it, there are multiple traces associated with a test case. And to compute the fitness value of a test, we simply take the fitness value of the best single trace. In other words, we enumerate all the traces associated with a test, we compute the fitness values of each trace, and then we simply take the best fitness that's been computed so far. One problem is that properties may truly hold. So that these properties were initially inferred based on the initial set of traces, and it is possible that among the properties inferred, there are properties that are true of the software system in general, and they cannot be falsified, and a search goal cannot be covered. And it will be a waste of the search budget if we kept it as a goal that is targeted by the test case generator. So in DICE, we abandon the goal after some time. So this would allow the test case generator to refocus its efforts on other goals and focus on guiding the test to falsify the other goals that could be falsified. In our evaluation, we compare DICE against DSM. DSM is the deep learning based approach that uses random test generator to produce a large number of traces. In virtually every case study that we looked at in our evaluation, DICE outperforms DSM. So this validates our idea that a systematic diversification of traces can outperform when a large volume of randomly generated test cases. In conclusion, we have looked at the problem of mining automata-based specifications. To deal with the problem of limited traces that do not capture uncommon behaviors, we use test case generation, and we target the gaps in the diversity of the traces. We through an approach, a framework that we term adversarial specification mining. We implement our framework in an approach named DICE, short for diversity through counterexamples. So given an initial set of traces, they may not encode and capture all the possible behaviors. We try to mine LTL properties from the traces, and then we use test case generation that is directed at falsifying these properties. The idea here is that the counterexample traces are the gaps in the diversity from the initial set of traces. And along with the initial set of traces, these counterexample traces are then used to mine a new automaton model. And that is the end of my talk. I'll be happy to take any questions. Thank you for your time.
Good morning, everyone in Europe. Good afternoon in Asia. We are here with the first authors of this session, David, with Hong, and they want to answer your questions, the questions that I expect that will flow in through the chat. So please go ahead and make them. Okay. In the meantime, we will have a conversation. Okay. We were talking about flying and the good old times before the pandemic when we could meet together in conferences, physical conferences. But this year we will have to stick at we have the cloud art, which is pretty fun. Hong, David, I was watching your presentation before the session, and it's a very well defined piece of work. It's really hard to find. Actually, it's pretty straightforward. The concept is very simple, and the only thing that really I have a doubt that may be interesting to discuss. It's about the time and the ability of the algorithm, the genetic algorithm, to find those traces that are hard to find, because you know that there is no guarantee that it will happen. Do you have any idea about I don't know how to tell it, effectiveness, the ability to find in practice those strange traces that you are looking for?
Right. So I guess the issue is that one reason that you might have this doubt is that in our evaluation we only looked at relatively simple classes. But of course, in order to run the evaluation robustly, we had to run it many times. And even though they're relatively simple classes, we didn't spend a long time for each testing campaign. But in the end, it turns out that we were effective on all of these simple cases. And then afterwards, this was not in the presentation, but we also tried to investigate its practical applications, and we apply it to fuzz for protocol fuzzing. As it turns out, our tool works pretty well for FTP, so it does in fact work in practical cases as well, other than the simple cases that we looked at in our evaluation. So I guess that validates the idea somewhat that this would also work in practice, given that a set of conditions and we had to do some engineering to get it to work for FTP, but these are not fundamental limitations of the approach. For instance, we had the tool look up for exceptions to determine that a particular trace should end there, and that a particular behavior was not actually possible. But it is not necessarily the case that all software would behave like that. That it throws exceptions wherever something was not possible. But with that limited amount of engineering, we managed to get our dice to work in the case of FTP and in case of RTSP as well. So it does show that our tool would be effective, most likely for many practical cases as well.
Yeah, the practicalities is the key,
yeah.
Because we are this discussion about time is mostly theoretical. That's another theoretical question that I want to make, because time is one of the dimensions, and the other dimension is, how can I say, completeness. That is the ability to find, let's say, those strange traces out of the set of strange traces that we don't know. So it's the completeness is always a problem, because you don't know exactly when you have found everything. Do you have an idea have you explored that corner of your research?
So in fact, there would be an interesting future direction for us. But right now, it is difficult for us to try to validate this completeness, because these uncommon traces are also difficult for a human to think about. And we had issues trying to express these uncommon behaviors as well. So it's hard to say if our tool was really effective at finding all the difficult, uncommon behaviors. But that is something we'll work towards in future. In fact, that is the main research direction of this work. We're trying to address this issue. It's just that we're not aware of any ways to try to upper bound of this approach now, or to say what are the limitations or the theoretical limitations for understanding these difficult and uncommon behaviors.
David, please go ahead.
Oh yes, if I also may add, in terms of like the completeness and the soundness of the inferred specifications or the inferred models, actually we measure the precision, recall, and F1, which is kind of like an empirical measure of how complete or how good the model is. And so far, the result has been promising. Actually, the harmonic mean between this precision and recall is about 87% out of 100. For the many different classes that we investigate, and of course it's not perfect yet, But we actually demonstrate by using this adversarial specification mining approach, by generating test cases, we can actually boost the performance further than without having this feature. So we hope to actually investigate more, consider more different classes, and then see empirically how much more can we gain in terms of the completeness of the model that we can infer.
We have a question in the chat made by Nan Yang that you can read yourself. So if you want to read aloud, perfect. So you understand and enunciate at the same time.
If the context examples are used to avoid states that should not be merged, so the answer is yes. That is one use of context examples, but our context examples are also used for more than that. So in our specification inference process, we try to we characterize the states and in terms of the moment, so that the examples do have information. We have two states that are there from each other. Different methods are enabled at the different states. But the context examples are also used for more than that, because the context examples could give us other behaviors that could let us discover new states that we. I hope that answers your questions.
If not, they will tell. If not, they surely write some petition for clarification. And I'm not working in this area, in model checking, but well, I do some things with my students, and well, I know a little bit how it works. And well, in terms of what do you plan to use this type of research and models for? Because, for instance, I'm used to model checking. Do you use the research to improve the ability to how can I say, verify real applications whose models are created not on the basis of a specification, right, but on the basis of a set of traces. What is the difference in terms, for instance, of let me make the question correctly. When you verify the behavior of the application, what is the difference between the before and the after with this new proposal?
So in fact, our approach wasn't targeted at the verification of software systems, although it could probably be used in that aspect as well, although we didn't explore in that area. So one thing we started off with was to use these models to try to look for bugs, API misuses, like misuses of APIs in which a user breaks an invariant of the API without realizing it. But in our experiments, we also found that these models could be used for fuzzing, because if by running our approach on a client of a protocol, like the FTP client, we could actually get a state machine that represents the FTP protocol, and we could use this in a fuzzer of an FTP server. So we found that it does help to improve the coverage. So I guess the idea of these specifications could be useful for different things. And one thing we explored in our experiments was to use it to explore programs in a deeper way, to explore more behaviors that a traditional fuzzer without using these state machines cannot explore as well.
And before going to the discussion room, Nan has some comments on your previous answers, so maybe you can consider them.
Right. So Nanyang's question is about could it be possible that a generated counterexample is not a real counterexample with respect to the system? So in this case, the answer is no, because the generated counterexample is a trace that we obtain by executing the software system. And because it comes from a concrete execution of the software system, this counterexample would be a real counterexample that is produced by the system. Yeah. So that's all for this question. And again, I hope I answered the question correctly.
He will be able to join the discussion room that we will have in a few seconds. David, please go ahead.
Yes, maybe Hongjin, you can explain a bit how is the counterexample is being generated, right? So you have a client program that you analyze to produce traces.
Right. So in this case, we worked with a kind of a simplified model of the software system in which we are only looking at the invocation of the methods. So a counterexample is the sequence of methods that are invoked by a particular class in our experiments. So these method invocations would be real because they would directly represent the possible methods, possible sequence of method invocation by that particular class.
Perfect. I'm going to close the Q&A here because it's 10 seconds to go to the discussion room. So I encourage everyone who is interested in keep on discussing about this work to join the discussion room with us.